All right, good morning. So today we're exploring the issues and impact related particularly to artificial intelligence. There was a question in last year's Year 11 exam about algorithmic bias. That was one that I predicted would come up, and it did. I don't think it's likely to come up again, but it is possible, and we definitely need to understand it. But issues related to it, I think, are likely to come up. So let's just get straight on with the Word document. This is P20. I won't record the part of the lesson where you watch the video. I'll let you watch that yourself. So I'll pause and I'll come back after we've finished watching it. So we've watched the video. Hopefully you've watched that at home. We'll go through, scan through. You can pause the video at any point to double check. This is what we've got. So I'd like us to spend some time looking at where AI has got things wrong. So I'm going to look at Microsoft's Tay chatbot. I'd like to do a bit of research. What was the algorithm used for? Each of these algorithms was biased. What caused the bias outcome and what happened as a result? So we'll explore one together, and you need to explore something else. So Microsoft Chatbot was pretty impressive technology. The idea is that people struggle with mental health or loneliness. They want someone to speak to. They don't want to have to wait until their friends are awake, until mental health services have the capacity to support them. They can speak to someone anywhere. Really noble idea. It's also able to learn, because artificial intelligence is not just pre-programmed. It can respond and learn. However, it learnt from the way that teenagers interact with each other. So teenagers hurled abuse at it. They tried to date it. They tried to insult it. And it learned from that language, and within hours, it was shut down because it had learned that same abusive behavior. So you can read more about it, explain what it was used for, why was it biased, because the training data was also biased and not filtered out. What caused that bias? Well, a lack of a profanity filter. It would still be possible to make this work if you put safeguards in place, but as we've seen with ChatGPT and other large language models, every guardrail and safeguard can be circumnavigated, as in you can get around it. It's really tricky to get it right. Because if you think about it, if AI mimics the way that humans think and learn, well, we haven't got a perfect recipe to produce a perfect teenager yet. There is no such thing. Every teenager makes mistakes. Every human being makes mistakes. We all say things we regret. If we're mimicking human behavior, our technology is also going to mimic the ability to make mistakes. And regulating that is infinitely harder than a procedural logic where every if statement is predetermined. There is going to be failure. How do we regulate that failure? How do we limit that failure? How do we mitigate it? How do we litigate it? How do we take it through courts and hold the right people accountable? So spend some time, research as many of these as possible, build them up so that if you have an exam question that is all about algorithmic bias, as in, is a algorithm more likely to give a positive or negative opinion about someone based on their age, their gender, their sex, their nationality, their ethnicity, anything like that. You've got case studies to refer to. So having a look at an example question here, we need to define what algorithmic bias is. Algorithms are step-by-step instructions to solve a problem and make decisions. Bias means you're more likely to make one decision rather than another. Algorithmic bias, an example of that might be if you're deciding whether or not to let somebody vote, it might be more likely to let somebody older vote rather than somebody younger. How and why? Because if the training data provided to an algorithm is exposed to more pictures of older people, it might not recognize younger people. What would be the impact? Well, it might suppress votes from one particular ethnicity or age or race or gender. How could you reduce the risk? By improving the diversity of the training data. Whenever you see a discuss question, you want to be balanced. You don't want to have just one opinion on one side of the argument. It can be good, it can be bad. However, this particular question focuses particularly on algorithmic bias, which is never a good thing. So you particularly want to focus just on the bullet points here. If the question was rephrased to say, discuss the impact of AI on the police force, that would be different. Then you'd have to say what's good and what's bad. So So there's some subjectivity in the answers here, because there's research into these happening all the time, but you could argue that at least at some point in the future you'd be able to tick all of these columns. Certainly for identifying cancerous tissue, AI is now more accurate than humans. Can it process more data in the same time as a human? Absolutely. It's the big advantage of AI. It might be expensive to develop, but once you've developed it, it's far cheaper because it can do much more than a human who requires years and years of training and salaries and holiday. Decisions can be almost instant. Not exactly instant. It takes a huge amount of computational logic and computational processing power to make AI machine learning models work, and that has an environmental cost as well as an economic cost. But nothing frees humans from danger. It might reduce the risk, it might increase the risk, it might change the risk. But life is full of risk. You cannot eliminate risk. You can only reduce and mitigate risk. So here's some examples of AI and machine learning. So we've got Silas here, who uses robotics and AI to create robotic lab assistants who can be more reliable and faster and more cheaper, I suppose, in the long run. He said career highlights are inspiring people about robotics. What else have we got? This is Aldo Faisal, whose job it is to make computers seem more human. So we can create artistic robots controlled by eye commands, which is rather exciting. We've got Jennifer using AI to make prosthetics better. What else have we got? Machines with brains. Yeah, nice. And robots that can function for environmental purposes in places that are inhospitable to humans. All right, so we've been chatting about what our priorities are for revision, and we've said the thing we're least confident at is IP addressing. So we're going to write some Python code to focus on IP addresses. So remember the 4-level model. You've got the application layer, you've got the transport layer, you've got the internet layer, and you've got the link layer. Routing happens at the internet layer. That's where we use IP, Internet Protocol, for our IP addresses. So what is an IP address? Well, we're going to write a Python program that correctly validates an IPv4 address. So feel free to watch this or to code it along at the same time. Hang on, I was talking whilst typing, never a good thing to try and do that. IP address equals, please enter an IP address. So our program should let you type in something and it's going to say that is not a valid IPv4 address. And then also you type in something that is a valid IPv4 address, which is a number between 0 and 255, a full stop, a number between 0 and 255, and that repeats 4 times. So an IPv4 address has 4 numbers, each of them between 0 and 255. So let's decompose the problem. Let's think about input, process, and output. We want to let the user type in an IP address. And our output should say, yes, this is a valid IPv4 address, or no. So we're doing some decomposition now, and we're splitting it up into different sections. We've got a global variable, something that stores something, and it's going to store a string, so we'll initialize it to an empty string here. How about something that we could reuse that does either this or this or this? What do we think would be a sensible subprogram? So we said we want to check and see if something is a valid IP address. We should probably specify that it's IPv4 because IPv4 is different. We've had a good question. What is the difference? Well, IPv4 is 1 byte, anything 8 bits, 0 to 255. Another byte, another byte, another byte. So that is 4 bytes. So that is 32 bits. 2 to the power 32 is 4 billion different devices. When the internet was first designed for ARPANET military purposes, the idea of having more than 4 billion devices connected to it was outrageous. But nowadays, when each person in a developed country will have, 10, 11, 12 different devices, and there's, 8 billion people on the planet, we have got more connected devices than we've got addresses to be able to allocate to them. So we've had to use some creative ways to be able to share IP addresses, like NAT. But we've also had to invent a new way of doing things, IPv6 addresses, where there are just more addresses to go around. But they're slightly more complicated to validate, so we're just going to keep it simple for today. So let's see. Here we can say if our IP address is valid. What is our IP address? Well, it's the return value from our thing here. Then we can say that our IP address is valid. Otherwise, we can say it's not valid. Can you spot the syntax error? What is the syntax error? Yep, so we've got an indentation error, else must be lined up with if. We've also got a syntax error because there's nothing defined here, so we'd better check and see, shall we? Let's think. Let's decompose this further. I'm going to split this into parts whenever you have a full stop. Check there are 4 parts. Check that each part is a number between 0 and 255. If we manage to do all of those tests, we'll consider it a valid IPv4 address. How do we do it? Well, we open the PLS and we take a look. Right, let's Control F in the PLS, search for split. How do we do it? We have a string, we split it based on a character. Okay? We've got a parameter. Let's copy that. That's the name of the string. We'll split it based on a character. We want to split it each time we get to a full stop. What data structure will parts be? Yes, we're hoping that parts will be a list that contains 4 values. So let's see. If the length of parts is not equal to 4, I'm going to say return false because it's invalid. We've got too many or too few. So that is this bit. Then we want to loop through each of them and check that there are numbers between 0 and 255. So let's see, for part in parts. We'll go through each of them. We need to get the value of it. Convert it. Part, there we go. We'll convert it to an integer. If the value is less than 0 or the value is greater than 255, common mistake here is to not be explicit. That's how you'd say it in English. If the value is less than 0 or greater than 255, it's not how Python would do it. You have to be explicit. So if either of those invalid cases are true, it's not a valid IP address. However, if it survives both of those checks, we can return a value. What value are we going to return? Here. Good, true. I reckon it'll work. That's invalid. Nice. That should be valid. That should be valid. That should be invalid. Good. How about 5 numbers is invalid. What's going to happen when I do this? It's going to crash. I mean, we could fix it, but it would be outside of the scope of the GCSE to be able to do that. But we could do, it'd be this line here that fails. We could say, try it. If it fails miserably, then return false because it's failed. It's not going to crash anymore. You don't need to know how to do try and accept for the GCSE. So let's see. It doesn't crash. It works. So what have we learned today? We have learned that an IP address is used for routing across the internet. You have subnets. So the first value will be like the main address, and this will be the least significant address. So think of it like country. It's not like country, but think of it like that. County, town, and street. So if you have 2 IP addresses, something like 192.168.1.1 and 192.168.1.2, they're on the same subnet. They're on the same place. They're probably connected to the same router because most of the IP address is the same. However, if it's on a completely different, if the first number is completely different, they can still be connected, but they'll have to be connected by lots of different devices. Remember, these IP addresses are included in the header of each packet. In the header of each packet, we need a source address and a destination address. It's like an Amazon parcel saying who it's to and who it's from. Everyone who handles that parcel is able to look on the envelope or the box and say, yep, I know who that goes to. I'm going to send it this way. I'm going to send it to our Peterborough delivery office. I'm going to send it to our London delivery office. I'm going to send it across to New York. Bit by bit, you point it in the right direction until it eventually arrives in the right place.